So in this video, let's talk about how many stereoisomers. How do we calculate the amount of stereoisomers possible for a compound? Now this is actually interestingly, this is actually carbone, and this is what's responsible for that nice aroma smell that you get in actually mint, right? So this is the active compound that's involved in mint, spearmint, to give it that aroma. Now we want to figure out how many stereoisomers we could actually get from a particular compound. And this video is, we know that formula to be certain. So the number of stereoisomers possible, right? This is just 2 to the n, where n is the number of Chiral centers. So the formula is pretty simple, right? So essentially, this video is really asking about how do you identify Chiral centers. Now, in a simplistic way, you should think about Chiral centers as, so let me draw carbon here, and usually, right, the chiral centers is usually carbon, but just remember it's not strictly pertaining to carbon, right? It could be anything that has 4 different things bonded to it. So essentially what I'm saying is that I have a carbon, I could have an R bonded to it, I could have an R prime, I could have an R double prime, and I could have an R triple prime, right? So that's essentially what I mean. Right, so there's 4 different things bonded to this carbon. So we denote this as the carbon being chiral. Now in organic chemistry, the idea is now, where in this compound do we actually see chiral centers? Right? Do we see any chiral centers at this carbon? No, it's a CH3. It has 3 of the same hydrogen bonded to it. Do we see a chiral center here? Well, first of all, it doesn't even have 3 things bonded to it. It's double bonded to a carbon, and it's single bonded to another carbon and 2 hydrogens, right? And I'm sorry, 1 hydrogen. So this is not chiral, right? Is this center chiral? No, this would not be chiral. It has 2 hydrogens on it, so 2 of the same thing cannot be chiral. However, this is chiral, right? And so this is actually chiral. This is our chiral center. Do we see any other pause the video and try to go through it. Do you see any of the chiral centers in the molecule? And it would be no, right? This has 2 hydrogens. It cannot be chiral, right? This carbon, again, it doesn't even have 4 substituents. It actually has 3, right? Double bonded to a carbon. It has a hydrogen and a CH3, right? And then this carbon obviously is not chiral because, again, we have 3 hydrogens. So this is actually the only chiral component in this structure. So we say the number of stereoisomers possible would be 2 to the n. So essentially we have 2 to the 1, right? Because we only have 1 chiral center. So the number of stereoisomers possible for carbone would actually be 2, right? Now since it's 2, we could quickly draw the other structure. And so the other isomers, and so the other isomer would look something like this. And this is the actual other isomer. Now, the video is not about enantiomers or diastereomers, but can you identify the relationship between these two? And these are actually enantiomers. Right? If you do it, you will see that this, and this is S carbone, this is R carbone. If you do your pre-log rules, you would see that this is the R version of carbone and this is the S version of carbone. All right, let's do another question. How about this one? This is actually Tamiflu, right? This is the brand name, right? And then we used to treat the flu, right? You go to the doctor, you have the flu, you know, cough and all that good stuff. They give you some Tamiflu for the influenza. right? So the idea is, how many chiral centers do you see? How many chiral centers do you see in the molecule? Pause the video and come back, right? I see a chiral center here, right? I have four different things bonded to the carbon, right? If I simplify, if I look at this carbon, which is a carbon of interest, I have the carbon in the middle. I have this bond right here. That's leading to something totally different. So I could say that's R. I have this bond coming down here. That's something different again. So this is, let's say this is R prime. Remember, I have a hydrogen as well, right? I have a hydrogen coming out. And then I have this R group, right? Totally something different. So let's say this is R double prime, right? So four different things bonded to this carbon. The same is also true for this one, right? This is also a chiral center. The same thing is true for this. This is also a chiral center, right? I have four different things. I have an amino group, have, a carbon with a CH2, I have a carbon with two different substituents, right? And then I have a hydrogen, right? So this is a chiral center as well. Do we see any more chiral centers in the video, in a compound? Yeah, this would be one as well, right? Again, four different things bonded to this central carbon, right? We have this group, we have a CH group, we also have obviously this big group here bonded to this carbon, and then we have a hydrogen coming out. So four different things. Are there any more chiral centers in the molecule? And the answer is actually no. So the number of chiral centers, number of stereoisomers that we would get would be 2 to the third power, which would actually be 8. Right? So really, you gotta train your eyes to see the chiral centers.